In this lecture, we are going to look at the noise and offset of the telescopic OpAmp. Now, before we do that, it is a good idea to review the noise of a cascode amplifier, of a simple cascode amplifier. So, the way we are going to do this is we are going to find out the effective input referred noise, because as we have studied before, the input referred noise tells you how much noise is contributed by each set of components in the circuit. So, to do this, we are going to look at the short circuit noise of the circuit. So, since that is an easier way to do this, I am going to redraw the small signal equivalent circuit with the output short circuited. So, we want to find out the short circuit noise, and in this particular case I will use this polarity for a very specific reason. We will find out I squared SCN, and if I divide I squared SCN by the square of the transconductance of the cascode amplifier, this will give me the input referred noise voltage squared, which I shall call En squared. So, to refer this back to the input of the amplifier, I will divide by the square of the transconductance. And as we have seen, the transconductance of the cascode amplifier is nothing but Gm1. So, this is I squared SCN over Gm1 squared. Now, let us take the noise from each transistor and look at how much of it flows through the output. We will first start off with the noise from M1. So, now the noise from M1 is IDN1 squared, and this noise splits between transistors M1 and M2. Now, if you look at the way it splits, the current will split in the order of the impedances. The impedance looking down, which I'll call R down, is nothing but the RDS of M1. The impedance looking up, which I'll call R up, is nothing but 1 over Gm2, because I have a short circuit at the drain of M2. So, this means Gm2 is much larger than GDS2, 1 over Gm2 is much smaller than RDS1, and this means that almost all of IDN squared flows into M2. The complete current flows through M2 and flows into the short circuit. Therefore, the first component of the noise, I will call that ISCN1 squared is equal to IDN1 squared. Now, let us look at the noise from M2. So, if you look at the noise from M2, that can be represented by a current source across the drain source of M2. And we want to find out how much of this current flows through the short circuit. So, we want to find out the component flowing through the short circuit. To do this, we will use a small trick that we have used before. So, we know that a current source between two nodes can be represented by a series combination of the same current source. So if I call that I can replace that with two current sources I with no change in the circuit. And again, this can be changed as two current sources I with a short circuit at the common mode point. So and there is no current through the short circuit. Therefore, the circuit does not change at all. We are going to do the same thing here. So we are going to change this circuit to the following. I'm going to show the two current sources in red and blue. So we are going to split this current source. The only difference being these two sources, red and blue sources, are going to be correlated noise sources, and I'll call that I1 squared, and the red one, I1, and the current in red is flowing into the source of M2, and that will be called I2. And remember, this is equal to I1. And I'm interested in finding the overall short circuit current. So if you look at I2, or rather if you look at I1, let's look at I1 first. So I1 has the option of flowing down into the drain of M2 or up into the short circuit. Of course, I1 will prefer to flow into the short circuit directly because it's the path of least impedance. So there is a current I1 flowing in this direction through the circuit. Now what about I2? If you look at I2 also has the option of flowing through two paths in the circuit. It either has the option of flowing upwards or flowing downwards. As we have seen, the impedance looking downwards is RDS1, whereas the impedance looking upwards is 1 over GM2, which is much smaller, and therefore this current is much larger. The impedance is much smaller, so I'll just point out that this is a low impedance. Therefore, as seen in red, I2 flows in this direction. Therefore, ISCN2 is equal to I1 minus I2 is equal to 0, since I1 and I2 have the same magnitude. This means that the noise from the cascade does not appear in the inside the short circuit. So the noise from even though the cascade produces noise, its noise does not appear at the short circuit node. It keeps circulating inside the device, and eventually if you measure the input referred noise, you will find that the cascade does not produce any noise at all. So therefore, En squared is nothing but IDN1 squared. So ISC squared over GM1 squared. This is nothing but IDN1 squared over GM1 squared. And please remember that IDN1 is 8 KT by 3 into GM delta F. So this is 8 KT by 3 GM1 times delta F. So the power spectral density is 8 KT by 3 GM. As you can see, the input referred noise of the cascode amplifier consists only of the noise of M1. Even though you have added a cascode, the noise of the cascode does not affect the noise of the amplifier. Now we are going to use this to figure out the noise of the telescopic op-amp. So now let us now take the telescopic op-amp. You can see now that there are 9 sources of noise in this circuit. We will go through these transistors one by one and figure out how much of this current flows into the output. To do that, again, we will short circuit the output node and figure out the short circuit noise current. And we can refer that back to the input to figure out what the input referred noise of the telescopic op-amp is. As you might imagine, the noise of M0 is in parallel with which I'll call I0 is in parallel with M0. The impedance looking up through both sides is almost the same because it is 1 over GM1 versus 1 over GM2. So I will see equal and opposite currents, or almost equal and opposite currents, I0 by 2 and I0 by 2, and this current gets mirrored as I0 by 2 through M8 and M6, and therefore since these two currents are correlated, there is no short circuit current noise at the output due to M0. So there is a current I0 by 2 entering this node, and there is a current I0 by 2 leaving this node. So M0 produces no noise at the output. Now what about M1 and M2? As far as noise of M1 is concerned, you will find that this current has 2 paths to split. So we will now use the same method as we did for the cascode device. The reason we cannot use symmetry is because as far as noise is concerned, this is not a virtual ground, is not a signal ground, because of asymmetry. Of input signal. So in this case, the input signal of interest is what I shall call IN1. We are going to ground the gates of M1 and M2. As you can see, as far as the signal is concerned, which is IN1 in this case, the circuit is no longer has a line of symmetry, and therefore you cannot consider the circuit to be symmetric on both sides. The way we shall approach this problem is to change, is the same as before. We will add 2 current sources in series and ground the intermediate path, and we shall see how the signal travels through the circuit. So I'll show that in red and blue as usual. So I'll call that I11 and a current source I12, which are both correlated. If you look at I12 sees the impedance of M0 looking downwards, which is extremely large, and the impedance looking up into the source of M1, which is of the order of 1 over GM1, and therefore and the other side, which is 1 over GM2. So these are the 3 parts that the circuit looks, and it turns out that the current I12 will split equally between M1 and M2. These 2 parts are of course symmetric now. So now this current flows into M7. So this is I12 over 2, and therefore there is a current I12 over 2 flowing into the M8. What happens to the current flowing here? There is a current flowing in M2 of value I12 over 2, and that current flows into this, and therefore this current is 0, because by applying KCL at the output node, there is no current through the short circuit. Now what about the current source in red? You will find that this current has two paths to flow at this node. It can flow upwards, looking up into the source of M3, which happens to be a very low impedance, versus flowing down where it has a very high impedance, which is that looking down impedance at the drain of M1. Therefore, what happens is that most of this current flows from M3, and this current flows down through M7 and gets reflected through M8. So this current is I11. There is very little current flowing through M1, M0, M2 and M4, and this current flows through the short circuit. Therefore, if you look at the noise of M1, the short circuit noise current is I11, which is equal to IN1, the drain thermal noise of M1. So therefore, ISC1 squared is this is so ISC1 is 4 kT by 3 G1 delta F. So all of the noise of M1 appears through the output short circuit. You can do a similar analysis for M2 and show that ISC2 is also 4 kT by 3 into GM2 delta F. This is the squared noise at the output due to M2. Now, what about M3 and M4? You will find that noise of M3 and M4 does not appear at the output. This is because of the cascode action of M3 and M4. Because M3 and M4 are cascode transistors, their noise does not appear at the output. Now, what about M5 and M6? It turns out that same is true for M5 and M6. Noise of M5 and M6 does not appear at the output. Finally, we need to look at the noise of M7 and M8. So let us take the noise of M8 itself. We will show that in blue. The noise of M8 is a current source which is I8 squared in parallel with M8. And as you can imagine, I8 squared has two paths to flow. The impedance looking downwards is RD as 8, whereas the impedance looking down is 1 over GM6. So most of I8 tends to flow through M6 and eventually through the output short circuit. Therefore, I will say that ISC3 is equal to ISC3 squared is equal to I8 squared, and this is nothing but 4 kT by 3 into GM8 delta F. Similarly, you will find that noise of M7, which is I7 squared, also appears at the output. I'll call that ISC4 squared. This is I7 squared. This is 4KT by 3 into GM7 delta F. Finally, we know that GM1 is equal to GM2, GM7 is equal to GM8, and we also know that the overall transconductance of the op-amp is nothing but GM1. Therefore, we can say that En squared over delta F, this is the input referred squared voltage noise density. This is nothing but the total short circuit noise current divided by GM. So maybe first we will write down the total short circuit noise current. The total short circuit noise current is 16 kT by 3 into GM1 plus GM7. Therefore, the total input referred noise squared voltage density is 16 kT by 3 GM1 to 1 plus GM7 over GM1. Please note that this is very similar to the noise of the input referred noise of the one stage op-amp. So even though the telescopic op-amp has much larger DC gain, it has very similar noise performance, especially at low frequencies. Now finally, we will write down the expression for the offset without deriving it directly. I'll just point out that the behavior of an offset voltage or current is similar to that of noise. So I'll just point out that as far as offset is concerned, we are going to consider only VT mismatches. You will find that VT mismatch of M3 and M4 does not appear as an input referred offset. Just as their noise did not appear when referred back to the input, the VT mismatch of M3 and M4 is also reduced and does not appear at the input of the overall op-amp. And the same can be said for M5 and M6. So I'll write them in blue. So we will say that M3, M4, M5 and M6. This is similar to the that for noise. Now what about VT mismatch of M1 and M2? It turns out that VT mismatch of M1 and M2 appears directly at the input of the op-amp. And finally, VT mismatch of M7 and M8 is scaled down, scaled by the relative GMs when you refer it back to the input. So the input referred offset voltage, which is represented by its standard deviation, I'll say sigma squared OSN, has two components. The first component is the VT mismatch of 1 and 2 and the VT mismatch of 7 and 8 scaled by the ratio of GM7 to GM1 whole square. This is also same as that of one stage op-amp. So there are some parameters that are different for the telescopic op-amp and some that are the same when compared with the one stage op-amp.